Capacitors store energy. In particular, they store electric energy. This energy that they store is the same as the work required to move the charge onto the plates. So there's some work involved in moving those charges through some potential difference, and that work is the equivalent to the energy stored. And we did a similar thing last semester where we talked about, if you remember the lab where we had a spring and we had to calculate the work it took to stretch the spring, and that work was also equivalent to the potential energy that we could store in the spring. That's the same thing that's happening here. If the capacitor is not charged, you don't need much work to move a small amount of charge from one plate to the other. But once you get charge transferred, you start to develop a potential difference across those plates. V is equal to Q over C. That's us taking our equation for the capacitance, C is equal to Q over V, and solving it for the potential difference. So after your charge begins to transfer, you develop this potential difference. V is equal to Q over C across those plates. So work has to be done to transfer even more charge against this growing potential difference. If the potential difference is larger, you have to do more work to get that charge to move across the plates. So the total work required to charge a capacitor to its final charge is the area underneath the curve of this graph. And we've seen this before also. We talked about work as being the area underneath the curve of a force versus distance graph, for example. In this case, the work required to charge a capacitor is equal to 1/2 times the charge you can transfer divided by the potential difference. 1/2, well, because this is the graph that we can get whenever we start increasing the potential difference and start loading the charge onto the plates of the capacitor. It looks like this. We've got little increments of the amount of charge we can move. On the horizontal axis, and on the vertical axis is the potential difference required to move that amount of charge from one plate to another. And so this creates sort of a triangle shape here. All of this stuff under here is the work that is required to charge that capacitor. That's the area underneath this curve here. That's a triangle. The area of a triangle is 1/2 base times height. So then the work, if the work's the area underneath the curve, the work to charge this capacitor is 1/2 times the base here, which is Q, times the potential difference, which is V here. So that work is equivalent to the energy stored in the capacitor. And then, therefore, the energy stored inside the capacitor, the electrical energy, is 1/2 times the charge times the potential difference across the plates. Now, since we know that, well, we can rearrange this equation in a bunch of different ways. V is equal to Q over C, C is equal to Q over V. We could solve that for Q. Q is equal to C times V. So if we replace Q here with C times V, the energy that you can store on the capacitor is 1/2 C V squared. And let's see, what are we replacing here? V, we're replacing V in this equation with Q over C. So you replace V with Q over C, you have to square it. And then that also reduces to Q squared over 2C, or 1/2 Q squared over C. All of these equivalent relationships for the energy you can store on a capacitor are listed on your equation sheet. But also remember that the work to charge a capacitor is the area underneath this curve of the charge that you can move across the plates, and the potential difference required to move that charge. Now for your engagement check here, your concept engagement, I'm going to ask you this first question. We're going to think about it conceptually. You have a parallel plate capacitor, and it's going to be disconnected from a battery. The plates are pulled a small distance further apart. So we've charged the battery, we're removing it from the battery, and we're going to increase the distance between the plates. So after we do that, you're going to think about, do the following quantities listed here increase, decrease, or stay the same? So we've charged the capacitor, we disconnect it from the battery, so we can't put any more charge on it. And then we increase the distance between the plates. Does the capacitance increase, decrease, or stay the same? Does the charge increase, decrease, or stay the same? Does the potential difference across the plates increase, decrease, or stay the same? And what about the energy stored in the capacitor? So that's your question to think about. But for what we're going to work through together is this second example here. We have a fully charged parallel plate capacitor, and it's going to remain connected to a battery while we slide a dielectric between the plates. And then we need to figure out, do these following quantities increase, decrease, or stay the same? Okay, to think about this problem, we remember that we have a fully charged capacitor. We're going to keep it connected to the battery, and we're going to slide the dielectric between the plates. So if we slide the dielectric between the plates, remember that our capacitance is equal to, we've got our dielectric constant, epsilon naught A over D. So if we don't have anything between those plates, then this dielectric constant is just 1. So we're going to slide the dielectric in between it. It's going to have a dielectric constant of greater than 1. So that means that our capacitance has to increase anytime we put a dielectric between the plates. So for B, what happens to the charge? Well, we are going to remain connected to the battery. So that means that charge can continue to accumulate on that capacitor. And if that's the case, then we remember that the charge on a capacitor is equal to its capacitance times the potential across the plates. Now, this potential is fixed by the battery. It's fixed by the potential of the battery itself. So this quantity doesn't change here, as long as we're keeping the same battery. Now, since the capacitance increased, that means that our charge that we can store on the plate had to also increase. And well, I guess in answering this question, we actually answered C too. What happens to the potential difference across the plates? Well, as long as we're connected to the battery, that potential difference remains fixed. It's the same. Okay. And then D, how does the energy of the capacitor, the energy stored in the capacitor change? Well, the energy stored in the capacitor is equal to 1/2 CV squared. It's equal to 1/2 QV. It's equal to 1/2 Q squared over C. Well, I guess there's a bunch of different ways I could think about it, but if V remains fixed, remains the same, but the capacitance increases when we stick that dielectric in between the plates, then let's see, maybe I should write it like this. V squared remains the same, but our capacitance increased in this case. That means that the energy stored in our capacitor has to also increase. It increases because the capacitance increased, but our potential across the plates remains the same. Okay, so that's the thought process you want to use to think about the battery or the capacitor in the concept engagement question that I'm going to ask you. And in that one, you're removing the capacitor from the battery. You stored charge on the capacitor. Now you're going to disconnect it from the battery. And then what's going to happen? So some of these questions here are going to be a little bit different. The answers will be a little bit different for the concept engagement question that you have. Now here's an excellent FET simulation that shows us a little bit more about capacitors and how they store energy and how they kind of work in a circuit. Here I have my capacitor, and I'm going to, and I've got a battery here that I can connect that capacitor to. That battery is going to apply a potential across the plates of the capacitor that will allow us to store charge on the capacitor. And we can also get an electric field between plates. So I'm going to connect my capacitor to the battery here, and I'm going to turn the battery all the way up to 1.5 volts, all right? And then we see that we've gotten positive charges on the side of my capacitor, that's on the positive end of the terminal of the battery, and negative charges on the side of my capacitor that's on the negative terminal end of the battery. And I can increase and decrease the separation between the plates, can increase and decrease the area of those plates, and you can see how that changes the capacitance, right? The capacitance is equal to, or is proportional to, the area divided by the distance. So if our area gets bigger, our capacitance gets larger. But if we increase that separation, our capacitance gets smaller. So right there, it was showing it right there in units of picofarads for the capacitance. I can also take a look at the charge on the top plate here and the energy stored in the capacitor. So I can store more energy inside the capacitor when I've got bigger plates and I've got a smaller charge separation, because that's when we have a large capacitance. I can also show the direction of the electric field in between here. You can see the direction of the electric field. Actually, if I change the terminal ends of the battery here, this is our positive end of the battery and this is our negative end. I change the direction of the electric field inside the capacitor because it always wants to point from the positive plate to the negative plate. Put it back this direction. So now we've got some great charge stored on these plates. We've got some energy stored within our capacitor. And now I'm going to discharge this capacitor through this light bulb. This is exactly what happens in an instant whenever you turn on the flash of your camera. You're discharging that capacitor, discharging all that stored energy, electrical energy inside that capacitor. So I'm going to close the switch here. And you saw that very quickly I supplied energy, electrical energy to my light bulb, and then that energy gets sent out very quickly and it depletes the stored energy inside the capacitor. So now my capacitor no longer has any charge, it no longer has a potential difference across the plates, and no longer has any stored energy because it gave up all of that stored energy to light that light bulb. Let's think about capacitors in a medical device. Capacitors are necessary in defibrillators. This is a defibrillator because they can deliver energy far more quickly than batteries can. They can quickly release that stored charge, that stored potential. Batteries themselves provide a current, but they do that through relatively slow chemical reactions, whereas capacitors can release charge that has already been stored, again, super fast, and we'll see that in the lab this week. And if you don't know what a defibrillator does, you've got this device here that's, there's a capacitor in there. It has been fully charged, and we've got these little paddles here. These essentially act as parallel plates that you put on somebody's body, and you discharge the capacitor in that way. So you discharge the potential across the plates. You put those paddles, those metal conductors, onto a person, and you discharge the capacitor. And that sends a very quick potential difference through their bodies, and that can jumpstart your heart. Your heart is an electrical device. It works through electrical signals. And sometimes the electrical signals get all messed up, or they stop, or they slow down, and you have to jumpstart them. And that's what a defibrillator does. So a fully charged defibrillator contains 1.2 kilojoules of energy stored in a 1.1 times 10 to the minus 4 farad capacitor. Find the voltage needed to store 1.2 kilojoules in the unit. And let us work on that very quickly. There's a bunch of ways we can store energy in a capacitor. Remember that it's equal to 1/2 QV. It's equal to 1/2 CV squared, and it's equal to 1/2 Q squared over C. Now, in our problem, we are given an energy that we have to discharge, and that's essentially the energy in our capacitor, and that's 1.2 times 10 to the minus, or sorry, 10 to the positive 3 joules. And the capacitance of this capacitor is 1.1 times 10 to the minus 4 farads. And we need to find the voltage needed to store this 1.2 kilojoules of energy inside the unit. So 10 to the 3 is a kilojoule. We need to find the potential difference. Okay. Well, let's see. If I look at my equations, which equation am I going to use? I'm going to use the one. Well, we've got this energy, we've got the capacitance, and we've got the voltage. So I guess I'm going to use the second relationship here. So I'm going to use the energy stored in the capacitor is equal to 1/2 CV squared. We need to solve it for this potential across the capacitor. So I can multiply both sides by 2, and that cancels that half on the right. So CV squared is equal to 2 times the energy stored in the capacitor. And then I can divide both sides by C. The V squared is equal to 2 times the energy in the capacitor divided by the capacitance. And then if I take the square root of both sides, I can get rid of this squared right here. So the voltage needed to store this amount of energy is going to be the square root of 2 times 1.2 times 10 to the 3 joules divided by my 1.14, or sorry, 1.1 times 10 to the minus 4 farads. And that gives me a potential of 4.67 times 10 to the 3 volts. That's pretty big, but that's a lot of energy we want to store inside that capacitor. Now I'm going to be using the word voltage, potential difference, kind of interchangeably in order to talk about this V here, this potential or potential difference or voltage across the plates of a capacitor.